I would say, yeah, go ahead, get started. And
Okay.
Keegan, like, I know, I hope that you're also going to just say a little bit about how you got to be the one asking research questions and why this is what fascinates you.
Yeah, good question. Yeah, but I will talk about that a little bit. Sometimes I feel like, oh, I don't know how they let me get in here. You know, I don't know how I made it to USC. I don't know how I'm doing research. Sometimes it can feel like a gated community when you're from the outside, right? You're like, oh, how do you even get started working on something like that? Like, how do you even get started working on robotics or doing research or anything like that? But really, it's just asking some questions. If you have a teacher, you're like, oh, how does that work? How does that, like asking more questions, then they'll be like, oh, do you want to work on it? And then you kind of get started on it. I could go on a tangent and talk about like how to get involved in research and that sort of thing, but I will try to stay a little focused here. Let me share my screen real quick. Hopefully you all can see the presentation. I think so. Perfect. So as it says, multi-robot systems, flying drones with the ACT Lab. So ACT Lab is what we call our lab. Boskin and I are both part of the lab. My name is Keegan Strawn, and feel free to ask questions any point during the presentation or also afterwards. Feel free to reach out to me and ask me any questions about anything, whether it's research, university, or robotics. Yeah, I would love to answer any questions. I won't promise that I'll have answers because I don't know everything. I definitely don't know everything, but I will at least try, or help you find the answers because I'd like to learn too if I don't know the answer. This is our lab. So when I talk about ACT Lab, it's the automatic coordination of teams. This means sort of just how do robots work together and how can we make them so they can work together by themselves? So we're not like controlling them to work together. We're letting the robots do the work for themselves. And we have our professor, Nora Ayanyan, on the left side there with the drone hovering above her hand. She is a fantastic person, very smart person, and she sort of runs our lab. And she's like, you could think of her like the manager, the leader, or what have you. And she mentors our group. She helps sort of set the research direction and our goals and mentor us as we do our research as PhD students and as grad students. On the top row, you can see Alahe up here. She is our postdoc right now in our lab. A postdoc is somebody who is completed undergrad, completed master's, completed their PhD, and now they're spending 1 to 2 years doing more research and mentorship of PhD students before they try to become a professor. Starting from the left to the right here, we have our 6 PhD students that are currently in the lab. We have Libby here on the left, Jingyao in the middle, Eric on the right, Boskin, who's sitting next to me, but also bottom left photo, myself, bottom middle, and then Connie on the bottom right. Great people. We have a lot of fun working together, and the main goal of our lab is multi-robot systems. My professor has told me, like, as long as the problem has more than one robot, you can work on it. Like, she's got funding for you to work on it. So that's great. There's a lot of really cool, interesting problems in situations where you have more than one robot. Yeah, so real quick, I'll talk a little bit. I am a second-year PhD student. I don't know if I mentioned that. So I was a terrible student in high school. I don't know if I should say that, but I was a terrible student in high school. I thought I wanted to like play ice hockey and do theater and like really far away from anything STEM at all. I'm impressed you all are in a computer science course in high school because I never did that. So you're already far ahead of me. And then I got to college, I started computer science, and our whole lab generally works from the computer science side of robotics. So we work on the software that goes onto the robots that control how they think, how they move, what they plan to do, that sort of thing, how they communicate. You might ask, like, why have multiple robots? Why not just build one giant, like, Terminator, superhuman robot, right? Well, that could be very difficult. It's hard to make one robot that's good at doing everything. So you might want to make multiple robots that are good at doing one thing. If you think about this, like instead of making one chef that is really good at making everything, you could maybe make one chef robot that does the like flipping of the patty, and then one chef robot that like grabs the bun and places the patty on the bun, and one chef robot that like puts the ketchup and mustard on it, or what have you. That kind of breaks the problem down into smaller problems that are easier to manage. So that's sort of one idea of why you might want to make a multi-robot system rather than a single robot system. And then here I've got a little video. I hope the sound plays, but I'm not entirely sure if it will. It's just got some music, so it really doesn't matter. And the way this worked, the reason I'm putting this in is because you can see robotics still has a lot to go. Like they're still failing at some very simple tasks, like walking over an uneven surface, just walking at all, opening a door, turning a knob, that sort of thing. They're still failing. And if a robot fails, and this robot is what you've spent years working on, and you know it's like the critical part of the entire sort of thing you're doing, then the whole thing is a failure. So one thing you might want to do is have multiple robots, so you sort of have this like backup, right? So if this robot fails, you have another robot that might be able to take its place or still achieve the goal that you're working towards. And then also, if the task is more complex than just simply opening the door, maybe you need multiple robots to move a box that's too heavy for one robot. Or maybe you have you need to press a button in 2 different locations or transport 2 different people at the same time. You're obviously going to need more than one robot, because a robot can't be in this 2 different places at once. So there's a lot of reasons why you might want multi-robot systems. Even if you do single robot systems really, really well, like if you're NASA, then you still might want multi-robot systems. So NASA makes these phenomenal like rover robotics, right? Like phenomenal rover robots. They still are thinking about how they can work in the sort of multi-robot domain. So they spend a lot of years, a lot of time, a lot of money putting all their eggs into one basket on this rover. And if that rover fails, then that's like a big loss for them. So they might not want to send that rover off down into some little cave and some dangerous environment, or maybe it's too large to even go there. So what if they created multiple small robots that they could place onto the rover, and then it sort of hops off the rover and explores Mars. And if we lose 1 or 2 of them, it's really not a big deal. And we have somebody in our lab working on the puffer system. They look slightly different than they do in this video now, but it gives you an idea of some other sort of robotics. And you could imagine multiple of these just sort of exploring, sharing the sensor readings that they get back, sharing the information, passing that data, and working together to sort of explore Mars. So another idea of where multi-robot systems come into play. Even if they're NASA and they're really good at making a single robot, you still might want multiple robots. And I also just like the little puffer robots. I think they're kind of cool. Yeah, so again, robots can look very different. Maybe you weren't expecting a robot to be like that small little puffer, but there's more than just the humanoid robots that we think of. So if you think of like multi-robot systems, and you're imagining like from the iRobot movie with Will Smith, where there's like rows and rows of robots. I'm probably too old that like you guys haven't seen that movie. I don't know. But robots can look different. So like here we can see Boston Dynamics, which is a robotics company. They have this Spot robot, very, very cool robot. It looks kind of like a dog. And you can see this one's opening the door and enabling this one to move through. I don't know if I'll even play this video, but you get the idea. Over here on the right, we see an image of like an Amazon warehouse. So like these robots are on the ground. They're fairly small at the bottom, the orange ones, and they've got these sort of stacks on top of them to transport items. So you put the items on there. The robots have to figure out, okay, I've picked up this item or multiple items, and I have to figure out where to put them in the sort of supply chain. So they have to move them around this warehouse. And not only are they doing this for themselves, but they have to think about not colliding with the other robots, not colliding with the people in the environment, and how you're going to plan all of this movement and all of the different tasks that these robots have to do. And then also like in the bottom right, we have the like Roomba robots. So like the vacuum robots. Maybe if you have one of these, it's just trying to map and vacuum up your space. But if you had multiple, they could work together to sort of say, I'll vacuum over here, you vacuum over there, and we can like team up to get this job done faster. And then also you might not think of it, but autonomous vehicles are robots. You can imagine in the near future where like we have a lot of these autonomous vehicles moving around. They could be communicating and collaborating so that we have better traffic. We have safer driving. They're able to like plan together how they're going to drive and move through. They might even talk with the street signals and different sensors on the road. They might communicate even with the phones directly. So like if you pick up your Lyft, it'll just come pick you up, and they can really plan everything and work as a giant multi-robot system. yeah, I'll do a quick summary of multi-robot systems and what I've talked about here, and then add on a little bit too. So benefits is that sort of robustness. This means like if that one robot were to fail, you have other robots that could take its place. And then it's also obtainable. So usually making that, instead of making that one very expensive like chef robot that does everything, and it might not even be possible to do that, you can make these smaller, more simple robots that are able to do this. But now you have to think about new questions, like how are they going to work together? How does the like patty flipping robot know to then transfer it to the other robot? How do you work the timing? How do they communicate? So there's other new questions to think about, even if it is a more obtainable problem to solve. And then sort of with that, it's modular problems. You can break it down, and that can maybe make the problem easier to solve. Areas we think of as we're doing this research is I put it under planning in general. People might debate this. You know, planning, collaboration, communication, control are all kind of separate things, but for this talk, I'm putting it as one, which is just under planning. So I want us to be thinking today about how are robots like thinking about what they're doing, but in a team sense. So how are they planning as a team? This takes collaboration, this takes communication and control. It's very hard for like humans to work together as a team. It's even like harder, sometimes easier to make robots work together as a team. But that's sort of what we work on in our lab, is how are they doing this? And then questions we might ask ourselves as we're working on these research problems is like, what connectivity do the robots have? Are they on Wi-Fi? Are they like connected to each other through like radio, or how are they communicating? Can they communicate at all? Maybe they can't communicate, and yet they still have to work together. And then also heterogeneity. So are they heterogeneous or homogeneous robots? Are they exactly the same? So today we're going to fly 3 drones that are 3 quadrotors that are exactly the same. You could exchange them and there's really no difference. They all are the same model. They all fly exactly the same. But you could think of a system where you have multiple different types of robots. So maybe you have like a ground vehicle that's moving through a space, and then you have a drone flying overhead, and you have maybe like a humanoid robot that like hops off the ground vehicle. I don't know. That's real sci-fi stuff. But you could have multiple different types of robots with different types of sensors, different types of cameras, different types of connection that they have. You sort of have to think of that as you're planning and setting up these problems. And then you have to think about scale as well. So are we talking, like my professor said, more than one robot is multi-robot? Is 2 robots is multi-robot, 200, 2,000? There's sort of a similar area of research, which is kind of a subpart of multi-robot system, which is swarm robotics. So swarms are like very large scale usually. So they'll have like 2,000 robots, and it's based off of, well, it's inspired by nature. So thinking about like ants and bees and the different colonies and hives and stuff like that, and how they have these simple little worker ants that follow a set like simple protocol, simple rules to follow, which may be like, go out here, grab this, bring it back. And it's very simple, but then together as a whole colony, it's complex behavior and they make some really cool things. So how can we take that idea into robotics? So if we have a robot that just does one very simple task, but we have like 1,000 of them doing it, it can then from something very simple create something very complex and useful. And that's sort of swarm robotics. Multi-robot systems is slightly different, but we have to think about the scale of things, how complex is each robot, and there's a lot of questions beyond the 3 that I've put here that we have to think about. But I just wanted to mention a few. Here's what we actually work on in the ACT Lab. So we do work on quadrotors, and that's why we're flying some today. We work on like trajectory planning and optimization of those trajectories. I'm sorry if you hear some noises. There's like sirens and going off. Hopefully you can still hear me. I'll talk a little louder maybe. There's learning for controls, mixed reality. So we do like a lot of cool different things there. Learning for controls is just like, how do they learn to fly for themselves? So maybe they could learn to fly, but then also like if they get disturbed by either like wind or even like a person coming up and knocking it, is the drone able to like self-correct and stabilize itself? And then also perception and communication. So SLAM is short for simultaneous localization and mapping. It just means if you were to put this robot out, can the robot figure out where it is and then also build a map of where it is? And we look at it in the multi-robot sense. So if you were to put multiple robots out there, can they collectively think about where they are and build a map of the space? So if you're deploying this puffer system onto Mars, Can they like find key landmarks and stuff to sort of recognize where they are and build a map? We also work on some ocean monitoring projects. We work on MapF and MapD, which is just planning. It's multi-agent pathfinding. So planning the paths that like the Amazon robots have to follow in order to deliver this item over to this location, but you have maybe 100 of these in the Amazon warehouse. And so you don't want them to collide. And I'll talk about that in a second too. And then multi-agent collaboration as well. So like, you probably have heard of like AI and machine learning and computers sort of learning what to do. Robotics uses this too, so robots can learn what to do. What happens when you're trying to have multiple agents doing that, multiple robots doing that? So can they learn the shared tasks together? Do they learn individual tasks that combine into the group tasks? Adversarial games, so maybe they're competing against an agent or anything like that. And then human inspired algorithms as well. So sometimes we're not sure what to do. Maybe we're like, we can find some inspiration from how humans collaborate. And so we look at that as well. Here's a video, so it's a little less boring of a talk. You can actually see some quadrotors fly here. This is in our warehouse, so that's where I'm currently at and where we'll be flying the drones today. You can see them take off, and then they plan their pass through so they don't collide with each other and they don't collide with the obstacles in the space. And then they reach their destination on the other side here. And it's just really cool. They light up. I think they look really cool. And then they come out on the other side and spell USC because we've got to have that school spirit here. Yeah, and so you can see this is actually operating on the real robots. One thing we do is work in simulation first. So here you can see a simulation of the same exact problem. So working on real robots can be expensive and it can be dangerous and it can be difficult. You might want to, when you're just testing out an idea, try it out on simulation first on a computer. So you can see the simulated drones are these little spheres, and then they're going to their goals over here. And they plan their paths and move through the area just as they would do on the real robots. But they're able to do so. If you're testing out this algorithm and it might not work, it most definitely will not work because we usually have a lot of problems we have to work through. You can at least do this in simulation where it's not going to hurt anyone, not going to break any robots or do anything like that. And then you take this and you transition it over to the real robots. I saw a question come in through there. I'll pull it up on this screen here. Do you recommend a simulation website free? There are a lot of different simulators. I don't know, Boskin, what would you say?
Yeah, we don't use websites for that, but we use like simulation software. Like for example, there's Gazebo that we generally use, and this is probably in Gazebo. And there are like visualizers as well. Sometimes like you do simulation, but you don't have a simulator. You assume some kind of physics and then just code it and visualize the result in some other program. So for that, you can check Arvis. So there's Gazebo for simulator and Arvis for visualizer.
So there's different applications, and if you Google them, they will probably come up. And they have like different introductions and tutorials and stuff that you can follow. And I recommend you do. It's kind of fun to do, and you can do that all just through simulation. Yeah. So, oh, here's another crazy swarm video where they're just flying up, getting into a formation, and they rotate. We actually had the world record for a while for the most drones flown indoors. We had 50 of them flying inside the warehouse here. And you can see them here rotate. And we like to show this video off because it just looks cool. It's not quite like a hard research problem because they're not doing anything too complex, but it is cool to see. And then we do some like trajectory planning work, which again, you can see in simulation as the drones fly, they're like correcting their trajectory and trying to avoid other people and have a smooth path to their destination. This is SLAM, which I talked briefly about. So the simultaneous localization mapping. If a robot sees this image, how can they tell where they are, what they're looking at, that sort of thing. And so they can use what's called LiDAR, which is really just lasers going out, and they can find points on the environment that then they sort of relate to like a LiDAR map of the environment with these different points. You can also have like a stereo camera view. So this is just a camera view that then finds these points and then work together to sort of like collectively find key points that you can use to localize where that robot is. And so the green things are kind of like these key points it's finding. MapF is what I also talked briefly about, which was really just collision avoidance. So if in the classic MapF problem, you've got like this mouse up here, mouse number 1, and then you've got mouse number 2 over here on the left. If mouse number 1 is trying to reach the cheese number 1, and mouse 2 is trying to reach cheese number 2, the initial plan might be, oh, just have mouse number 1 move forward, and then move forward, and then over to the right, and then down to cheese 1, and have 2 do the similar thing. But you'll notice that at time step 1, so once they've taken 1 step, they would both collide right here in this space. So you would want the mouse to maybe mouse 1, they need to coordinate, and mouse 1 will say, oh, I'll go first, I'll move here, and then number 2 can go through. So 2 has to wait first. So that's sort of some planning and some collision avoidance for the paths in this small sort of environment where they might collide. So over here in the middle, you can see a sort of colorful example where these agents are just squares. So we can represent robots as something very simple, like a square, moving to circle destinations. And they're in a very dense, close-knit environment where they're going to collide. So they have to plan their paths in order to get there without colliding. And this is relevant to like robots that might be working in a warehouse. So this looks more like a warehouse where they're having to reach a point, pick up like an item, and then transport that item somewhere else. And that's sort of the MapF problem. I think the colorful simulation looks really nice. I told Eric in my lab, who is mostly working on this, that it looks great and he should submit it to like an art exhibit for like technology and art. And if you like blew it up and you made it really large and you just had them all planning their paths, I think there's maybe something creative and artistic about that. And you can maybe find meaning in it. So yeah, that's why I put this in here. And then we, like I said, we look at human inspired stuff. So we had a group of people play this game where this is their single person view looking down at the ground. They can see somebody standing off beside them. It's like the person's foot, and that's all they can see. And then in the overhead view in this little black square, you can see the 4 different agents moving in the environment. And the agents are given a task to like build a shape. So here you can see much more agents working together, and they have to build a sort of like square-like shape, and they finally reach building that shape. So these are just humans doing this through like an online game. And okay, there. And so now you can see like we get this data, which is just humans moving around. We look at how they're doing this and we try to find like different aspects of it, different key things. So you can notice like some of them, most of them have just stopped moving. They're just standing still. And then like one of them's off here in the distance, some are like rotating around and moving around, and then some are like nudging the other people and trying to get them engaged and moving, right? We can take that and look at it and go, okay, we see these like types of roles these people are taking on. And so maybe we can use those roles to inform robotics and how we might work together in a collaborative environment. And so like the yellow ones are just sort of standing still, the green ones are kind of wandering, and the pink ones are kind of like nudging and moving people, taking on maybe like a leadership role. And so, yeah, that's an overview of some of the projects we work on, and then maybe where are we doing it. So we do it in a number of places. So like here is our cage is what we call it. It's a smaller thing than the warehouse here. And the cage allows us to test out this software on drones because, like I said, it can be dangerous and expensive and different things like that. And so we can put padding down in here and have the drones learn to fly. And if they crash, they're not going to break themselves, and they're not going to break anybody else. They're not going to hurt anybody else. It's also difficult to fly drones outdoors because of like government and like aerospace regulations and stuff like that. You can't just go fly drones out in the air in the airspaces, and you might collide with other things and get into trouble or hurt somebody. So that's no good. So we work in like set spaces that we control and can make sure are safe. And so this is one of them, which is our cage. And then we also do work that's not in like a lab type space like that. This is like our office sort of space. We sit here at desks and we work on the computer, and we will also like meet at the table and have meetings and do presentations on the TV. And we have these nice windows, and it just, to me, it has a little bit of like a startup feel. So it's almost like you're working at a company. You can collaborate with the other PhD students and talk, and we'll get lunch sometimes. And so it's fun too. We have fun here, is all I'm saying. And then here's the warehouse. This is where I am at currently. And I'll give you a little tour, actually. I've got you guys on my phone here. So hopefully I can take this and flip the camera around. let me see. I will stop. Oh no, I can keep showing. So I hope you all can see this here. Yep. No, I can see it there. I think it's fine. So you can see Boskin there. We can wave to Boskin. And then there's like, we've got a desk and computers here. Here is the warehouse, the main space where we fly. So this is our flying space. You can see we've got a little setup here. We've got some drones ready to go to fly. This is where we will be flying them. We've got a webcam so you all can watch it on the live stream. And we've got these tiny little drones. So we've got little crazy fly drones that I will show you closer up in a second. And then we have cameras you can see up here. These cameras are Vicon motion tracking cameras. If any of you have seen something like Planet of the Apes or even like The Lord of the Rings with Gollum or the Marvel movies, they will often use a motion tracking system in those movies to track the actors as they're moving around. We use them to track the drones. And so if we look down here, we can see they have these the little like gray dots on them. The cameras are able to track those gray dots and see the drones, and we can localize them based off using the multiple camera angles to figure out where the drones are. So we don't always use that data because you might want the drone to not be given that data. Sometimes in real life, a drone won't have GPS data or different localized data like in the SLAM scenario. So when we're testing them out, we won't use that data, but we will use it to like see if what our estimate is correct. So when you're doing research, you want to be able to say, is like where it thinks it is actually true? And so we can use the true value to check that and see how far off our robot is. And then I'll just show you around the space a little bit more. We have this little room here with some drones in it. We've got some larger drones here. We've got some even bigger ones up there. And then we work a lot with these tiny little crazy fly drones. So the brand, I think the brand is BitCraze, and then they're Crazy Flies. And they're very small little drones. You can see like the size of my hand here. And we got some other goodies and stuff just for the drones. And then we've got like a computer workspace area. Before COVID and the pandemic, we'd often have people working in here, but we have a kitchen and a microwave and a sink. And it's just overall a pretty cool space. Yeah, and so this is where we're gonna fly the drones. I'm gonna head back to the desk. I saw some questions come through, so I'm gonna check those questions here. Flip the camera around. Okay, cool. Plug in my phone so it doesn't die too. There we go. Okay, so let me see here, questions. Can you spell the name? Oh, that was from the previous one. So gazebo and then RViz. So I'll put that into the chat. So RViz was the other thing we used for simulation. What brand drone? I think I talked about that. BitCraze and Crazy Fly. I think you asked that before I said it. So I can put that into the chat too. Is it Craze like that or AIZ?
Yeah, that's correct.
I'm just debating my spelling here. Crazy Fly. Do you guys do any modifications to the drones? We do modifications to the drones. Boston, do you want to?
Yeah, so we actually like just get the firmware of these guys and update them like whatever like in ways that we need. So this is the first modification we have. We generally make modification to software itself because we are doing research on them. And we put some stuff on them as well. So we have like these small cameras that we can put on drones. So we put these on as well to like get some video feed. So yeah, like we don't do a lot of like electronic stuff because like the electronics are fixed actually. Like we have some motors and a processor, and you just control them. So there is not like a lot of need to do modifications there, but we mainly do modifications on software. Yeah.
Yeah. So again, we work mostly on like the software side of it. So we're not working on like the actual hardware, making a lot of changes there. Although there are research labs that do that. So that is definitely a thing. But yeah. There's another question. That's a ton of drones. Yes, that is a lot of drones. We have, I don't know how many we have in total, because sometimes they like break and we exchange them and stuff. Do the size of the drones affect how easy they are to fly and control? Yeah, definitely. They also just, in some ways that you might not think of, like also the battery they can carry. So these small little Crazy Fly drones have very small, tiny little batteries that we put on them. And if it's just sitting still and turned on, it can last for like half an hour. But when it's flying, they can last for like max 7 minutes. So they don't last very long. And so that would be a big deal if you're trying to put this into like real life and put it into a real application. But it's also a big deal when we're just doing research and things like this, where we have to constantly be exchanging batteries. Going on a much smaller scale with the drones. So this is like as small as we go. There are other, is this the one? Yes, that's, yeah, Crazy Fly, yep. There are other smaller drones out there. People make their own that are very small, but that's not quite what we do here.
So about like the easiness of control, like there's also safety issue as well. So for example, there is a hole in the warehouse that I put while like flying a very big drone. So like if you're not like careful, you can actually hurt yourself really bad. Like when these small guys collide, they don't break and they don't like do any damage. But when the big ones fly, I can like very big problems. So
yeah. So if we're like putting on software to control the very large drones, and it's like software we haven't quite worked with, you know, it can be very dangerous, because if that runs into somebody or even into the wall, like Boston was saying, up into the roof, it can do some damage. But these little guys, we can fly these around and they really don't do all that much damage. So that's partially why we work with the smaller drones. What is the name of the other simulation software besides Arvis? Is what we also use in combination. Yeah. Okay, so I'm going to explain real quick the puzzle so I can get you guys working on the puzzle, and then I'll answer more questions too, if there are more questions. So if we look at the presentation here, there's a place at the top to put in your name. Well, above that, actually, you'll see a live stream of the video of the warehouse. So you can actually see the drones fly. So when somebody solves it, I'm going to say, hey, this person solved it. Let's all watch the live stream, and then you'll be able to see the drones fly. Below that video, you'll see first name, last name. You don't have to put in your real name, but do put in some name so it can, at least I can tell who solved it. And then you'll see these 3 starting locations. So this is like the starting location for the red drone, starting location for the white drone, starting location for the yellow drone. You then have to solve this puzzle by moving these pieces. So these pieces rotate, so you can change the orientation of each piece. You'll notice that like this one piece is like a up and down vertical piece, so it is able to move along that black path. So you're trying to plan the path for these drones. You're kind of doing the work for the drone. And then once you click it, you'll see it'll flow through and turn yellow. So you're planning the yellow path here. You'll see there's like an elbow joint, so it's slightly different here. This piece, it's able to come in from the top and about to the right. If you rotate it, it'll come in from the right down to the bottom. And then you can see like a cross. And so one can actually go down and one can go across the horizontally. So it can go vertically and horizontally. The goal is actually to get this path all the way down to the location down here. So it's kind of cut off, and I'll show you in a second the full view. But there's a place for the white drone to go, a place for the yellow drone to go, and a place for the red drone to go. And so you're trying to get yellow to yellow, white to white, red to red. That's the goal, is to get the path all the way down there. And it's also kind of a buggy website, so I apologize. I've made this fairly quickly, but if you click things, they'll kind of reset, and hopefully you can get it to work. As long as the path is valid, it should still work, even if it's not showing the color correctly. You can always reload the website and make it work better. At the bottom, you'll see the button. The button will turn white when you have a correct solution. You'll also be able to hopefully tell that you have a correct solution. And then click that button, it'll send it off to me. And just for safety reasons, I have it wait to fly the drone. So I'll have to click yes, fly the drone now, and it'll fly the solution that you send to me. It'll hopefully be kind of cool and to see them fly, as long as everything goes according to plan, which sometimes they don't, but hopefully it will. If you have any questions about how to make this work, let me know. Otherwise, I will also share the link to the site in the chat. So if everybody wants to follow this link and open it up and start playing around with the puzzle, I'll be happy to answer any questions about the puzzle, about drones right now as we go. And if nobody ends up solving it, no pressure. I can make the drones fly without that. I'll have them fly a certain path to get there. And yeah, let's, before somebody, we need to turn on, so if you want to turn on the robot, I forgot we have to actually turn the system on. So Boskin's going to run over and turn on the robots. If you have the live stream playing, you might actually be able to see him move over and turn them on the website. Yeah, and I'll stop screen sharing here. I can figure out how. So I'll stop sharing. Perfect. Just doing some things to get it set up. Yeah, I changed the batteries. Again, talking about the batteries, Boston was like, did you change the batteries? Because they do run out pretty quickly. And if the batteries get low, they start to not fly as well. Yeah, I can totally share the website. Hopefully it's working. It's not working, I'm sorry. Oh, that's closing out of the chat. You would think I would know how to use a computer because I've been doing computer science for a while now, but no, I still struggle. There, I should be in the chat.
Did you share the website?
I did. Did it not go through?
Maybe you sent it to someone privately. I'm not sure.
Are you in the waiting room?
I
guess like
sent
they
it
don't
to-
see any of your answers.
Oh, see, I really don't know how to use a computer. Okay, I sent it to everyone in the waiting room. So if anyone's in the waiting room, they're going to be able to solve it. Let me, everyone in meeting. Okay, there we go. Thanks for clarifying that.
And then you read the other answers as well then, because like they don't see them as well.
Oh,
Bit
and
phrase,
that's why
phrase.
you keep asking about the, okay. So I'll type those back in. So bit, praise, and harvest. Is there anything else? Oh man. Okay. Okay, great. Okay, everybody can see that. Cool.
Oh, I'm on my school laptop and LAUSD blocked the website, so
Oh, it did?
yeah.
Oh no. I can share my screen and then you can at least see it. Yeah, thank you for speaking out and letting me know about this. Okay. Here you can at least hopefully see the screen.
You can
so-
send the live stream link as well.
Yeah, and I can share the live stream link too.
That's bad. Like we can set another DNS from another domain if you have one.
Well, it's being hosted on a different site, so it's on GitHub. So that just I can't think of it. I'm sorry about that. Hopefully somebody can actually. We did the session on Tuesday and people were able to play it, so I'm hoping somebody can. Otherwise, I can just make them fly, but that's not as fun as having you guys actually get to do it. If you want just the live stream link, that should be the live stream link. And you can see I can like press this and the path starts to flow. I can move it around. Just because I'm using school laptop. Oh. But it's not easy. Yeah. I've had my friends all try to play it and they've struggled playing it. So maybe I should have made it slightly easier, but I don't know. You guys are smart, probably smarter than I am, so you can probably figure it out. But if nobody does, I can also give hints since I'm sharing my screen. The path for the red path so far is correct. Maybe give like a little bit more set time and I'll give a little more hints. Oh, block the live stream too? Oh, man, they just really don't want me sharing anything. Well, hopefully you can see the my screen sharing though, at least. Is anyone able to? Oh wait, this just said Chris solved it. Chris, you solved it. Great job. So if everybody wants to turn their attention to the live stream, either via my screen sharing, or if you are able to see the website, then
make it full screen.
yeah, I can make it full screen now. Good idea, Boston. Now I will let it run. So this is Chris's solution, and hopefully the robots fly. So you can see them take off here, and they kind of go up into the air. They're moving along the grid, along the path that has been solved. They're trying not to collide, but because it's been solved, it's probably not going to collide. One of them actually flies up here, so you can see it go up into the air, which is kind of exciting to avoid the other drone. There's a bit of a delay, so I'll let it just run. And then they make their way to the bottom and to the correct positions. See them fly. So great job, Chris, on solving that. You did that really fast, actually, and pretty good timing because now it's 11:49. So nice, well done. Yeah, so I don't know timing wise. I think last time I had to finish up a little early and then had to do a survey or something. So we could always run them again if people want them to run again, but I think I'll just leave that here for now. And I want to see if anybody has any questions or anything that I can maybe answer. And the cool thing about the live stream is you can actually back it up a few seconds if you missed it, and you can rewatch it. So if I were to put it back here, we can watch it fly again. I think it's much more impressive to see this in person. So I wish, the pandemic and stuff wasn't happening for many reasons, but also just so you guys could actually be here in the warehouse and see them fly in person, which I think is a lot cooler. And
well, robotics Ed Week is every year. So
next year you guys can do it.
I'm fine if we want to go a little longer, if it's up. If it's fine with you, Keegan and Baskin, and also with Ms. Stone's students, they probably have a period that's ending.
We have a little bit of time, so we can definitely go for another 15 minutes.
Cool. Now I have a question. How is it? What language, or I don't even know if that's the right question. How are you getting the drone? What are you doing with software that's getting the drones to communicate?
Yeah, so we're not controlling them in any way. So we're not sitting over there flying them with like a controller. I'm not just secretly hiding a controller over here and flying them. So the language that we're using to program them, it's kind of like you could use different languages to program any drone. So this is the way we're doing it. So I'll talk for how we're doing it here. We have C and C++ that runs on the actual drones. And this is like the sort of software that is making them fly. And then we have Python, which sort of acts in between, and it tells them like fly, like you could say like fly to here or fly there, or if you're wanting to give them different like high level commands and collaborate and communicate. So there's sort of like all those three languages, so like C, C++, Python, and that's pretty common just in all programming. Like those are pretty common languages, and then also for robotics, it's common languages. Any block programming? By block programming, do you mean like I think that's like the learning through like like Scratch? No, not really. I think there are other drones out there that you can actually, or like at least robots, ground robots that you can buy that are programmed through that, and you can learn to program a robot with that sort of style. Parrot, yeah. But ours are not that way. We sort of coded ourselves. or use the software that we get maybe off online to work with them. What does the problem solving process look like in your team, and are they programmed together or in separate programs? So I'll answer the second one first. Are they programmed together or in separate programs? Right now it's like one Python program. Well, actually, so there's a website, and the website has like web design, JavaScript, HTML, CSS that then sends off the path that you have figured out and sends it over to my server. My server interprets that through a Python program. We'll like check it and do stuff like that, ask me if I want to run it or not. And then it sends that to the drones, and it sends it to all 3 drones. And then the 3 drones are each receiving that through their own programs, which is like the C and C++ on each drone that then is running, and they will then fly, and it's each individual drone. So they're not even collaborating or communicating here with each other. They're communicating with the server. So it's multi-robot system collaboration, but through sort of like this middle person, the server, which is still common. It's still multi-robot system. They don't necessarily have to communicate with each other. They're still working together as a multi-robot system, because then we're thinking about the algorithm and software from like a centralized view. So from the server, how we get them to move without colliding. What does the problem solving process look like in your team? These are all great questions. Problem solving process can look very different depending on what lab you're in, who you're working with, and stuff like that. Right now, we sort of work mostly individually. So like, if I think of a problem, maybe because I'm reading a paper or I'm watching a video or I'm attending a talk or something like that, I'll have like an idea and I'll be like, ooh, maybe I could like change this and make this work slightly differently. Or maybe it's an idea like, oh, I see this opportunity in this one industry, like you could change that maybe. And so there's like a lot of different ways the ideas can come to you. And then you might be like start trying it out, just maybe like through like thinking about it, and then trying it out like in simulation or on the real robots. And then you have to collect data and results, and you go through the whole scientific method and write a paper. And then you will submit that paper or present your work somewhere. And that's sort of like the general like way it flows. There's also like a lot of collaboration. So when we are sitting in the lab together or on Zoom together, we'll like discuss ideas and like, what if we did this? What if we did that? What if we sort of do this? And then we'll work together. So like, there's some like, oh, you work on this part, I'll work on that part, or maybe it's more even collaborative. I don't know, Boston, if you want to say anything about the problem-solving process.
I mean, yeah, you mentioned about like, I'm actually like interested about like other question. Are they programmed together or separately? So we do both actually. Like as Tegan said, in this case, we have a central computer. They're sending the commands, but we also do like distributed planning. So in that case, like every robot plans for itself, and we assume that they can sense the obstacles around, right? And you can like still, even without communication, you can still cooperate with other robots. For example, like one of the assumptions you can have is that you can assume that everyone is running the same algorithm. So then you can have some mathematical properties that actually allows you to be sure that you're not going to collide just because everything is cooperative. So we do stuff like that as well, which is like really fun. And about communication, we communicate over radio. So like Crazyflies have these like radio dongles. It's like Wi-Fi extenders actually. They have the same idea. It's just a radio, and we send commands over the radio to Crazyflies. But of course, we also work on stuff in which like Crazyflies plan for themselves. With the assumption of sensing the other guys around, and with the assumption of cooperation.
Hopefully that answered the 2 questions. I think the problem-solving process can look very different for each person. Sometimes you're sitting in class and you have an idea and it can change. Yeah. It's a lot of trial and error. We fail a lot. We're like, oh, we could even spend months on something and then realize that it didn't work or that it failed. And then you have to sort of change your idea of thinking. Maybe you found this like roadblock and I got to go around it. Can we play the game again? Yes, we can play the game.
And also, Keegan, I'm just eating a little snack. I love what you just said about failure. And at 1 o'clock today, part of the Robotics Ed Week, we have a session called Permission to Fail. It's run by the people at iRobot. So you showed a Roomba earlier. So if anybody's interested in that, and if you're free at 1 o'clock, I will put a link in the chat to how to sign up for that. And so back to you.
Yeah, that sounds like a great. That sounds like a great sort of talk. That sounds really cool. I suggest you guys attend. Boskin is going to run over and reset them. It might take a little bit of time here, but hopefully not too long. So I'm just resetting some of the programs that I have here on the computer that help run the server. Is the line? Oh, the live stream's behind. I need to catch up. Yeah, I can check. They're like 3.9, so one of them's kind of low on battery. 10. We're gonna replace the batteries real quick, just so they make sure they fly correctly. Again, that's sort of they die pretty quick battery wise. Live stream's taking a while to load.
While we're waiting for the new batteries, Ms. Stone, do you think that that the way your intro to CS class, that your students are understanding this, or if your students want to unmute just real quickly to say if this is pretty much making sense?
I would love to hear from my students. I think this has been great. So yeah, if we could have my students comment, that would be wonderful.
Yeah, I understand that the drones still need some form of human interaction to communicate. Like when Chris solved the puzzle for them, the drones are just acting out on his problem solving.
Yeah, so yeah, you're exactly right. The drones are here using some form of like human interaction to solve this problem that they have. And the problem is the getting from the starting location to the end location. This sort of taken into our research would be like, how can the drones do it themselves? So maybe if the drones like had cameras and could like look at the different cells they were in, figure out how to get there without colliding all by themselves. So there would be no human interaction. And that's more what we work on. It's just more fun to have you guys sort of do that part of it and think about what it takes for that. So that was a good insight there. Nicely put. Okay, I think Boss, I don't know why the live stream is, at least the one I'm having here, is slow. Okay, there, we can see it back. I will start this. And if we want to find a solution, equal. I also know it's 12:01 now, so if you guys have to go, I don't want to keep you.
We can show this stuff as well. Always want to see.
Oh yeah, I can show you guys sort of what we see here in the warehouse. Let me switch the screen that I am sharing. This might be cool to see. This is like the view that the motion tracking software sees. So there's like an origin, like an initial middle position that is in the middle of the room. And then you can see it sort of tracks these lines to the drone. So we can see drone 10 here over on the left, drone 25 in the middle, and then drone 17 on the right here. And so we're getting this data from the cameras. The cameras see those little, almost little like buttons, those little like spheres that we put, oh, here's these like little spheres here that we put on the drones, and they are able to localize them, figure out their location. And then as they fly, you would be able to see them move also in this sort of virtual visualized environment. And this is RViz actually, which we were talking about. as the software we use. Looks like Maria solved it, so I can run them again. And I'll actually share this view of it, unless somebody wants me to share the other view of it. So we can see them fly up, and now they're moving across, and moving all around the area. Maybe I'll just a quick way to switch to the other view. So good job, Maria. Nicely done. They're flying correctly and getting to the destination, it looks like. I can even stop sharing and I'll jump back to the live stream. So if people miss the live stream, I can show that. You can see they've landed. We back it up. See them flying and moving through the space. Nicely done. So if I'd put more work into this, I could have had them maybe like fly back and reset their position themselves, but I didn't do that. That's definitely something. Keep losing the chat. I'm just really terrible at Zoom. Well, it looks like it didn't miss anything. It's okay. Okay. We're still, as you can sort of see from my talk, like a pretty long ways off of like the, if you know Terminator, like Skynet, and like robots taking over. But there's a lot of really cool problems that we're solving, and open problems for like years to come that we'll be working on. And then another thing, even if you're not interested in like the engineering side of it, we're going to need people that sort of work on the like policy and law side of it. So like we currently have the technical capability to have drones flying around and like delivering packages. But it's just harder to think about like, how are we going to make sure it's safe? How are we going to make sure that it's like legal and that nobody's going to get hurt when you have drones just flying around delivering packages or delivering a pizza? And how are we going to convince people that this is a good thing or that it should be allowed or that it's not going to like take over the world? Or, you know, how are we going to implement policy so that bad things don't happen as artificial intelligence and other things develop? So we need people that not only are like developing the technology, but people that also understand the technology and think about how we are going to sort of make sure that this technology benefits everybody and it benefits us as a society and everybody moving forward into the future. Yeah. So there's like other things to think about too. And then the cool thing with robotics is it kind of is very interdisciplinary. So if you do want to work on the hardware or the software, or maybe you even want to work in like marine biology, but you might end up actually dabbling in with some robotics because you might need them to go and explore the underwater and different things like that. Or, you know, there's just so many areas that technology is now prevalent. And you guys know this being younger, like you've grown up with tech. Like it's just everywhere. And if you're interested in like nature and like preservation and climate change or anything like that, really, like there's technology there and there's even robotics there to work on. It's really like spans everything and it'll just keep getting more and more that way. So yeah, we can wind up.
So that was so cool. And it's really amazing to be able to give directions to fly the robots from our homes. That's really cool. I've put into the chat box a link to a really quick survey. It really helps us for you to fill out the survey because we need to be able to prove that people are coming to this. And so you help us do more things like this by clicking on that and doing a real quick survey. And also earlier, I put the link to our other events. Like I said, at 1 o'clock, we've got Permission to Fail with the iRobot people. Tomorrow, we've got a few more sessions. We've got how to start a robotics program at your school. So maybe Mr. Palomares is interested in that one. We've got a fellow talking about how he went from building robots in his basement to building robots for the movies. So please check them out and come to more sessions. And then the final job I need to give you all is a job that we can all easily do. And that is, let's thank Keegan and Baskin for a really wonderful session. I learned a lot. Thank you. You could put thanks in the chat or unmute.
This was really interesting.
Cool. Yeah, glad you guys enjoyed it. Yeah, thanks for coming out here and watching it, virtually. I'm sure it gets difficult to just keep being on Zoom, but thanks. Yeah, hope you got something out of it, and feel free to even ask any questions. You can probably find my email on the lab website and everything. But yeah, thanks for attending.
Everybody can always reach us at k12stem1@usc.edu if I could pass questions on if you want.
Yeah, that'd be great.
So terrific. Thanks so much.